everybody, this is Mrs. Dinkelman, and this is the notes for lesson 4.2, L'Hopital's rule. Marquis de L'Hopital is the name of a mathematician who published this rule for the first time in a book, so that's why we call it L'Hopital's rule. And it looks like Le Hospital, but on spelling wise, a lot of times you'll see it with the little hat over it, so it's L'Hopital's rule. Anyhow, this is a rule that we can use to help us find limits. We're going to kind of go back to the limit idea, but it only works some of the time, which is one of the reasons why we don't teach you right away. The second reason we don't teach it right away is because you have to know how to find the derivative. So now that we are pretty good at finding the derivative, we should be able to use L'Hopital's rule in the situations where it works. So you can see here that we can only use it in really two situations, and that would be if when we try to plug in the value that they're giving us, that we would get an infinity over infinity or a 0 over 0. What I would like to mention is for infinity over infinity, I tend to like to do top heavy, bottom heavy, or equal instead of doing L'Hopital's rule. Just because it seems easier, like I just can look at it and decide what the answer is. L'Hopital's rule will prove that we're right. And remember also with the top heavy, bottom heavy, or equal, I like this acronym, NN-FEPL, that helps us to decide which functions grow faster or slower so that we can decide if it's top heavy, bottom heavy, or equal. So L for logs grow the slowest, and then x to the x's, which we don't see very often, and factorials, those grow the fastest. E is exponentials, like e to the x, and p is polynomials. Okay, so what L'Hopital's rule basically says here is that if we have a 0 over 0 or an infinity over infinity case, instead of trying to find the derivative in its, or the limit in its current form, we can take the derivative of the top and the bottom separately, and that will give us the same answer for the limit. And it's because of how functions grow and that their slopes will be similar as well. Notice this is not quotient rule. It's literally the derivative of the top and the bottom separately, and then we see what we can do with the limit. Okay, so let's look at a couple of examples. So example 1 here. First of all, this is a limit at infinity, so my preference would be to think about top heavy, bottom heavy, or equal. And if again we look, we can see we're comparing an exponential and a polynomial, and the bottom one is heavier, so that means this should be a 0. But let's look and see if we try L'Hopital's rule. So sometimes I'll write like an LH, so that if you look at my work, you can tell that I did L'Hopital's rule. I don't know if Gary does that or not. So derivative of x is 1, and the derivative of e to the x is e to the x. And I think we still need to know this idea of bottom heavy, because now we have 1 divided by something really huge, which would be 0. Same thing on number 2, except for it's reversed now, so now it's top heavy, so I think our answer should be infinite. And if we do L'Hopital's rule, the derivative of the top is e to the x, derivative of x is 1, and again we just have e to the huge number, which is just going to be infinite. So I didn't say this, but my brain did notice that this would be an infinity over infinity, this number 1, if I were to try to plug things in. Same with number 2, infinity over infinity. On 3, if we try to plug in a 0, we're going to have 0 over 1. And in 0 over 1, we just get 0. And we would not be allowed to use L'Hopital's rule because remember, we only get to use it in 2 cases. 0 over 0 or infinity over infinity. Okay, so let's look at 4 and let's verify if we can use this or not. So e to the 0 would be 0, so this is, or would be 1. 3 minus 3 would be 0 over 0. So we do get to use L'Hopital's rule here. This is not a top heavy, bottom heavy, equal one because it's not a limit at infinity like those earlier ones were. Okay, so let's just take the derivative. Derivative of 3 is 0. We have to use chain rule here a little bit, so let me talk it out for a second. So there is a negative 3 hanging out there, and then the derivative of e to the 3x would be e to the stuff times the derivative of the stuff. and then the derivative of x would be 1. And what's really cool now about L'Hopital's rule in this situation is we kind of eliminated our problem here. There's no longer a problem plugging a 0 in. So now if I plug a 0 in, e to the 0 is 1, and I just am left with a -9 over a 1. On number 5, what they want us to do is to not use L'Hopital's rule, to go back to the strategies we would have used in the last couple of units. So we would have factored here. So we could factor out a 2, and then we could factor that difference of squares there. Okay, and so we would cancel, and then we would plug in the -1 there. So it'd be 2 times -2, which would be -4. Or we could use L'Hopital's rule, because if I try to plug in a -1 right now, I'm going to get a 0 over 0 issue. So let me do L'Hopital's rule. Derivative of the denominator is just a 1, and then the derivative of the numerator would be 4x and then -0. And guess what happens if we plug in a -1? We also get -4. So it doesn't matter which strategy we use. Again, L'Hopital's rule, though, only in those 2 instances. Okay, this is kind of at the bottom of your notes and then a little bit at the top. So again, don't use it just because it looks like you can. It has to be one of those 2 options, a 0 over 0 or an infinity over infinity. And then the next statement there is sometimes it might be helpful to do this a couple of times. So what I mean by that is, let's look at 7. If I want to try to do this just by direct substitution, -infinity squared would be infinity, and e to the -infinity is infinity. And this is one of those that we kind of struggle with because it's a negative infinity. So it might be helpful now to have this strategy just to double check that we have what's right. So if we do L'Hopital's rule, because it does fit in the category, we get 2x over -e to the -x. Okay, so now if we try to plug in infinity, guess what? We're still going to get, well, at least -infinity over -infinity. So it still really fits the strategy. I can still do L'Hopital's rule. So I'm going to do L'Hopital's rule again. So limit as x approaches -infinity. So now this would be a 2 over e to the -x. Now if I try to plug in infinity in -infinity now, I get 2 over e to the infinity. So I cannot keep going because I'm not infinity over infinity anymore. But now it's a little bit more obvious to me that I have something that's bottom heavy. So it's just going to be 0 as my answer. Okay, so let's see, let's just verify on number 8, do I actually get to use L'Hopital's rule? So natural log of 1 is 0, minus 1 plus 1, and then 1 minus 2 plus, so it is a 0 over 0 case. And we can go ahead and do L'Hopital's and see where that leaves us. So derivative of natural log is 1 over x and then minus 1. And then this is going to be 2x minus 2. And so now if I try to plug the 1 in, I get 1 minus 1, which is 0, and 2 minus 2, which is also 0. So we can still do L'Hopital's rule. We're going to do it again and see what happens. So in my mind, I'm thinking of this 1 over x as x to the -1, just so you know, as I'm taking the derivative. So that derivative would be -x to the -2, and then divided by 2. That's the derivative of the bottom. Now for me, before I want to plug this in, I kind of don't like that it's a negative exponent. So my brain kind of wants to do one more step here. You don't have to do this. It's just something for me I prefer. I like it that way, and then it would just be -1/2 as my answer. Okay, so don't get tricked, by the way, on the assignment. Double check that it's either 0 over 0 or infinity over infinity before you decide to do L'Hopital's rule.